The last session, we had defined the turn on time of an SCR as a summation of delay time, rise time, and spread time. And we had defined the delay time as the time interval between the instant at which the gate current reaches 90% of its final value and the instant at which the device current reaches 10% of its final value. So basically, we defined the delay time TD as the interval between 0.9 times Ig and 0.1 times Ia. Similarly, we had defined the rise time as the interval between the following instants, that is the time taken by the device current to rise from 10% to 90% of its final value, or alternatively the time taken by the device drop VAK to fall from 90% to 10% of its initial value was the rise time. And we are told that the rise time is inversely proportional to the magnitude of Ig. That means larger is the magnitude of the gate current above 0, faster will be the lesser will be the rise time. And finally, the spread time is the time required for the SCR drop VAK to drop from 10% of its initial value to the on-state drop of an SCR, that is 1 volt to 1.5 volt. And we thus told that the on time T on is equal to TD plus TR plus TS. Now the definitions of delay time TD, rise time TR, and spread time TS as mentioned above have to be represented in the form of waveform. So we are having basically four parameters: the gate current Ig, the device current IA, the device drop VAK, and last is the power dissipation across the device, also known as the switching power dissipation. So now, as defined, what we will do, first we will indicate the delay time. So delay time is the time interval between 90% of gate current and 10% of anode current, right? Fine. So we will mark these levels, that is 90% of Ig, that is 0.9 Ig. We will also mark another level, that is 10% of Ig. Similarly down, we will also mark 90% of the steady state value, V in upon Z. Similarly, 10% of the steady state value of device current, V in upon Z. Yeah. Again, similarly marking 90% of the initial value of VAK, 10%. Yeah. Right. So this is the point which represents 90% of Ig. This is the point which represents 10% of Ig. Okay. So now understand one thing, that when the gate current reaches 90% of its final value, that is the time instant at which the anode current starts increasing from 0. Okay. Okay. So this is the instant at which the anode current will start increasing. So anode current will be 0. So till the gate current doesn't reach 90% of its final value, anode current will not start increasing. So the time interval between the anode current IA reaching 10% of its value and the instant at which the gate current reaches 90% of value is called as a delay time. So now the current starts increasing gradually and say it reaches 10% of its value here. Okay. So this will be the delay time. I'll represent it now. This is delay time TD. Okay. Now the rise time. So the time interval between 10% of IA and 90% of IA. Here. So this is 90% of the anode current. So this will be rise time. TR. Now rise time is also the time taken by the anode to cathode potential to drop from 90% to 10% of its value. So students understand that the instant at which anode current reaches 10%, that is the instant at which VAK reaches 90%, right? So at this point. And this instant last is the spread time, that is the time taken for the anode to cathode voltage to drop from 10% of its initial value to a value equal to onset voltage drop. It is this particular. Okay. Yeah, so maybe this point. Spread time TS. So we need to denote it. So this is 0.1 IA, 0.9 IA. Okay. Coming to power dissipation, yeah. Okay. Now we come to dynamic turn-off characteristics. So once SCR starts, latches, better than telling that conducting. Once SCR latches, gate terminal loses control over the device The only way to commutate the SCR is to make the anode current IA less than the holding current. This we already know. Third, however, if a forward voltage is applied immediately after IA becomes equal to 0, it will not block applied voltage, but will start conducting again. Okay, this is important. So now the status in point number 3 is that SCR is actually commutated, but it has just commutated. So after the anode current has dropped below holding current, or it has become equal to 0, if we apply a forward voltage between anode and cathode, that is anode positive with respect to cathode, then there are chances that the SCR will start conducting again. That means what? Just because IA has fallen below holding current does not mean that the SCR has completely turned off. It is in the process of turning off. That is why we say that the turn off time of an SCR or the turn off time of any semiconductor device is never ever 0, just like turn on time is never equal to 0. That means, to conclude with, that any semiconductor device takes a finite amount of time to turn on and turn off, but will start conducting again because SCR has not completely turned off. Because SCR has not completely turned off. So thus it is necessary to keep the SCR reverse biased for a finite period of time known as turn off time. So now, just like we define turn on time as a summation of 3 intervals, that is delay time, rise time and spread time, similarly turn off time is also defined in that way, but the constituents are a little different. So turn off time is defined as minimum time interval between the instant at which IA becomes equal to 0 and the instant at which device is capable of blocking the forward voltage bracket Ig has been made 0. Okay, so turn off time is defined as the minimum time interval between instant at which Ia is equal to 0 and instant at which device is capable of blocking the forward voltage in absence of gate drive. Okay, so just like turn on time had 3 components, turn off time has 2 components. So we can say the turn off time is made up of 2 intervals, namely reverse recovery time TRR and second is gate recovery time or recombination time. Or recombination time. This is my anode current IA. This is time axis. Device voltage VAK. Okay. So first I'll draw the characteristics and then we can explain it. So this is T1 in the middle, T2, T3, T4. So from T1 to T3 it is called as reverse recovery time, and from T3 to T4 that is called as a recombination time. One more time instant. TQ is called as a circuit turn off time. This is the on-state drop, that is 1 to 1.5 volts. T1, T2, T3, T4, T5, and we have reverse recovery time, recombination time, and circuit turn off time. Forward voltage, reverse voltage. So now we'll give some description about what is happening at what instant of time. So we see here it's very clear that at instant t equal to t1, the anode current becomes 0, and during the reverse recovery time, anode current flows in the reverse direction. Okay, so we see here this indicates is equal to 0. Okay, so we can say again below x-axis it's reverse current, above x-axis forward current. Right, so from T3 to T4 the current is reverse, it is negative. At t equal to t1, IA becomes 0, and during reverse recovery time, IA flows in reverse direction. At t equal to t2, it is here, we see here what is happening at t equal to t2. So at t equal to t2, reverse voltage is getting developed across the SCR. At t equal to t2, So when I say reverse voltage, VAK, it falls below 0, and current continues to reduce. At t equal to T3, the SCR junctions J1, J3 are able to block a reverse voltage ब्रैकेट में one important point here is due to the presence of excess charge carriers at junction J2, SCR is unable to block the forward voltage. Tenth point is during the interval T3 to T4, recombine at t equal to t4, recombination is complete. At t greater than t4, at t equal to t4, at t equal to t4, SCR is completely commutated. Hence, beyond t equal to t4, forward voltage can be reapplied and will be blocked by SCR. Okay. So an important comment here is okay. So what is the turn on time of an SCR? 1 to 4 microseconds. Hence, you can say the turn on time of an SCR This was a very important topic, dynamic turn on and turn off. I know that this is today is our 27th or 28th lecture, but it is worth because I have covered the most important concepts about operation of an SCR very slowly and in details. So beyond this thing, beyond this unit, when we go on to study all the different power transformers such as converters, inverters, AC voltage controllers, I will not have to spend any time for explaining the operation of an SCR. We can just draw the circuit, we can break the entire analysis interval from 0 to 2 pi into 4 different intervals, sub intervals, draw the equivalent circuits in the 4 intervals, draw the waveforms, derive the expressions, and we can conclude. Right? It may appear that we took a lot of time for covering unit number 1, but it was important. No issues. Yeah. Anybody has any questions to ask? They can ask. We have 6 more minutes to go. If anybody has any questions, they can ask.